Please respond.
Yes, ma'am.
Okay. So in the last class, we discussed about go back N protocol, right? In today's class, we are going to talk about selective repeat protocol. Okay. So why we went with selective repeat protocol? When you just see the go back N protocol, okay, the sender used to send multiple packets, okay, where by fixing up the window size, multiple packets were sent to the destination. But at the receiver was taking only one packet, right? That means the go back N protocol, it used to give a simplified work for the receiver. That means the receiver, he will keep track of only one variable or one packet. Correct, no? So if that particular packet is received, then he used to process and send it to the upper layer and receive the second packet. Though that he has received many packets, though it has been sent with multiple packets from the sender end. Okay, so in this case, the receiver was not required any buffer, right? Because he used to handle only one packet. Why he need a buffer? He was not at all using the buffer. The receiver, there was no need of a buffer. And in case if any out of packets, say for example, I used to send it in an order of 1, 2, 3, 4. Okay, and one should be received at the receiver first. In case if the second packet has arrived, okay, it immediately used to discard it because the receiver was not having any buffer, okay, and he was waiting for the respective sequence number. That is, if at all it is waiting for x plus 1, he would expect that packet only. In case x plus 2 has arrived first, the receiver would have immediately discarded, right? So there was no need of a buffer, and even the packets which were sent from the sender side, it was all, dropped. Okay, so here in this case, that is go back N protocol, the protocol is very inefficient. Okay, because there was loss of packets. The receiver was so flexible that it keeps track of only one packet at a time. Correct? In case, like, though that many packets have sent by the sender, if any one of the single packet is lost or corrupted, then the sender, he has to send all that n number outstanding packets. Remember, in case of go back N protocol, if at all there are like 4 packets are sent, okay, I will call it as 0, 1, 2, 3. In case at the receiver end, he might have received 0. Okay, then if at all 1 is lost, okay, then sender has to send the remaining outstanding all 1, 2, 3 packets to the sender. To the receiver, 1, 2, 3. From the sender, the outstanding n packets has to be sent to the receiver. Even though like some of these packets might have been received safe, okay, but the receiver used to discard it because he was expecting the very next packet. He can handle only one packet at a time, right? So that was so inefficient. Agree? If at all the network layer is losing some packets, okay, we are talking about the network layer. In case because of call it as congestion. Okay, some problem occurred, and because of the congestion, probably possibility that we may lose some packets. Okay, and in such situation, the sender has to resend all those outstanding packets. Fine, and in that situation, what happens? Imagine already congestion is there, and sender is sending all the remaining outstanding packets to the network. That means, don't you think that network load doubles? Yes or no? Because already congestion is there, because of which some packets are lost. Since packets are lost, now sender is sending all the remaining outstanding packets to the same network. So don't you think the network or the congestion becomes still more worse? Right? So again, due to that congestion, more packets are lost. Agree? Am I audible to all of you?
Yes, ma'am.
Okay. So because of which, that means like, I mean, this effect where I may lose more number of packets because of the congestion. Okay, so this effect, it may be like, you call it as something like avalanche effect. Okay, that sometimes this effect may even collapse the entire network. Okay, totally it collapses the network. Fine. So that is why the go back N protocol is quite cumbersome and it is very inefficient in handling the packets. Okay. Because of these errors, okay, that means like not errors, drawbacks, right? We need to have another protocol that has to be revised. Okay, and that protocol is nothing but selective repeat protocol. Okay, so hope it is clear why go back N protocol is inefficient. Any doubts? Any doubts?
No, ma'am.
Okay. So now what is selective repeat protocol? Why, how does it basically works when compared to that of go back N? Okay. And the name itself, you can see selective repeat. That means this is the revised version of go back N. Okay, here as I told you, the name itself is telling that it resends only those packets. That means only the selective packets. ಎಲ್ಲ ಪ್ಯಾಕೆಟ್ಸ್ ಕಳಿಸಲ್ಲ, ಔಟ್ಸ್ಟ್ಯಾಂಡಿಂಗ್ ಇದೆ ಅಂದ್ಬಿಟ್ಟು ಎಲ್ಲಾನು ಕಳಿಸಲ್ಲ, ಯಾವ್ದು ಲಾಸ್ಟ್ ಆಗಿರುತ್ತೆ. ದಟ್ ಮೀನ್ಸ್ ಲೈಕ್ ಇಟ್ ರೀಸೆಂಡ್ಸ್ ಓನ್ಲಿ ದ selective packets. Okay, those are actually lost. Understood why the name selective repeat? What you are repeating? You are repeatedly, I mean, sending the packet which are selective in nature. That means actually which are lost in the network. Right? Understanding?
Yes, ma'am.
Okay. So here you can see this is the outline of a selective repeat protocol where you could see the sender and a receiver. At the sender end, we are talking about the transport layer especially. So transport layer receives the information from the application layer where the segments are added with the header, and this header comprises of some information which is sent in multiple packets, right? So it is not that you are sending only one packet. Definitely you are sending many packets as per your window size and as per the request of the application layer, right? So now this is the segment. Okay, if I just talk, your segment comprises of like multiple bytes. If you consider, like we have fixed up the window size here. Now consider this is the sender window. Okay, and here at the receiver end, unlike your go back in, I was not having any window. It was only one packet which was received. Correct, no? But here, in order to avoid the inefficiency of go back in, we are also introducing the receiver window in case if any out of order packet or arrives. Okay, it will take it and store it in the buffer. It will not waste it. Okay, receiver will not drop those packets though it is correctly received and they are sound good. Okay, so it will store it until, if some respective packet is lost, the receiver what it will do, he will send information about only those which are lost and sender will send only those lost packets to the receiver. Remaining will be stored in the buffer. So there is a usage of buffer here. Okay, and you can see that the shaded windows, they define the packets that have arrived out of order. Okay, here say for example here it is shaded, right? So this is the packets which are arrived out of order. And similarly you can see here in this window, now I have sent some packets here, a blue color is shaded and this blue color, it is nothing but the packets which are sent, but they are still not acknowledged by the receiver. Okay, and the shaded portion, gray color shaded portion, this is a packet which is acknowledged but out of order. Okay, there is no proper acknowledgement received for that particular packet. Okay, now we know that sender will send multiple packets and each packet has a sequence number, checksum to check the error and the information, and multiple packets are sent from the sender to the receiver. Now the receiver will take all those packets and take it in an order. In case if any out of order packet arrives, he will store it in a buffer window. Okay, buffer. Now he will acknowledge again, not one at a time. In the sense he will also acknowledge one after the other as he receives the packets. And the acknowledgement comprises of acknowledgement number along with the checksum for acknowledgement. If the checksum for acknowledgement is not correct here, okay, that means acknowledgement is received, but there is an error. How do you know the error? By using the checksum. If the checksum is not matching, then the sender will discard that particular acknowledgement and ask the receiver to resend the acknowledgement. Or he has to resend the packet. Okay, so one of the cause will happen, right? Now, when you see the sender window, okay, this is the sender window for selective repeat protocol. And here also you can see that blue color shades, and these are the packets which are sent, but they are not acknowledged. And you can see there is a gray color packet which is received. Acknowledgement is received, but acknowledged out of order. Okay, that means he was expecting for 0, fine, but he has received for second. Okay, that means sender was expecting acknowledgement for 0th packet. But before that, he has received the acknowledgement for second packet. Okay, so this is an out of order acknowledgement. So he will keep it in its buffer. Okay, and the window will not immediately move to the next packet, next to send. Again, here you can see there are many variables, SF, SN and S size Okay, just like your go back N protocol, at the sender window, we have three variables. SF indicates the first outstanding packet to be sent or sent already. SN in the window size, okay, the window size, whatever you are fixing, some number of packets are sent, okay, and some number of packets still need to be sent, right? So that is SN is the next to send packet. Fine. It is a sequence number which indicates next packet to be sent to the receiver. And the window size, you are giving it as S size, and that is equal to 2 power m minus 1. Okay, the range we are talking here. And again, the sender window is segmented into 4. First is packets which are already sent and acknowledged. Second is outstanding packets which are sent but waiting for acknowledgement. Okay, because some are acknowledged, others are not acknowledged. So they are called outstanding packets, some acknowledged. And third segment in the window, packets that can be sent. That means it can be sent as per again the application layer request. Okay. Next segment here we can see that the packets cannot be sent, though it is there till the window slides over. Okay, it cannot be sent, right? Sender window for selective repeat protocol is clear. Yes. Any doubts?
No, ma'am.
Okay, because I need to keep on asking some people, please respond. Last lab session also I faced some network issues. Okay, I kept on explaining and later it was known that there was no network. Again, I had to repeat it. So it was messy thing. Okay, please, I'll be asking somebody, please respond it so that I'll have an interaction so that network is proper and you people are able to listen to whatever I say. Next, we are talking about the receive window for selective repeat protocol. Okay. See, in case of go back N, if you remember, okay, the receiver window, we didn't have something like this. That means we had only the R size was 1. Okay, we didn't have any buffer in case of go back N protocol. Remember, it was only one packet because the receiver used to never bother about the other packets which are received. He used to focus only on what he want at that instant. Okay, so that is why go back N. That means he used to whatever the packets, in case 4 packets are sent. Okay, he will take only 1 packet at a time. In case if one second packet is lost, the sender has to resend from the second 2, 3, 4, everything he has to resend it. Okay, so that was a flexibility which was given to receiver. But here in this case, as we know, receiver is also provided with the buffer. Okay, and also window size is fixed, right? So you can see there is a change in the receive window. Here I could see 2 variables. What are those? Rn and R size. But in the go back N, we used to have only one variable, that is R size. Agree? Sorry, R size was 1. The only one variable. This was a constant, only one. We used to have only one variable, that is Rn. Okay. But here you could see again we have 3 segments in the receive window. First segment, and this is a second segment, and these are the third segment, right? So when you see the receive window. Okay, it is as we know, it is totally different from go back N. Here the size of the receive window is same as the sender window. Okay, that means S size is equal to R size, and which is equal to 2 power m minus 1. Okay, and in case of selective repeat protocol, this protocol allows as many packets as the size of your window. Okay, that means say for example, receive window I have fixed to 0, 1, 2, 3, 4, 5, 6, 7. So 8. Okay, if at all 8 is there, then it can receive as many packets until the window is filled. Hope you are understanding. Okay, so until the size of the receive window is filled. Sometimes what happens, it may get some of the packets which are arrived out of order. Okay, in that situation, that will be kept in the buffer until there is a set of consecutive packets. That means the very next before and after packets are received. Okay, until it is received in an order or in a pattern or in an, what you can say, as per the sequence number, it will be stored or it will be kept in the window. Later it will be delivered to the application layer. Okay, and the first segment tells that packets which are received and already acknowledged. Okay, second segment, it is telling that packets that can be received and stored for later delivery. That means where it has to deliver, it should deliver for the application layer. Okay, and shaded box, here you can see the shaded box. These are the packets which are received out of order. Right, and there is a third segment in the receive window where the packets that cannot be still received. Fine, so the segment, if at all I take the segment, is having a sequence number. I'll tell sequence number is 4, so that means 2 power 4. 2 power 4 is how much? 16. Right, so 16, the range of sequence number is 0 to 15. Then 0 to 15, this is the sequence number, correct? What I'm talking, 0 to 15. In that I have fixed up the window size is 0 to 7, that is 8. Right, so initially we start with 0 to 7, or right. So what happens for 0 and 1, 2, as and when it is sliding over, window is sliding over. So 0 is received and it is sent an acknowledgement. 1 is received, then sent an acknowledgement. So 2 is also received, sent an acknowledgement. Now window slides to 3. Likewise, okay, once the complete process is done, the window keeps on sliding towards its right side. Right, so till the value of the sequence number is reached, then it will move on to the next sequence, followed by again 0, 1, 2, 3, 4, 5 up to 15. Hope you are understanding. Yes.
Yes, ma'am.
Okay, so here as I told you that sizes of the sender window and the receiver window is same. All the packets in whatever you have sent, okay, that means the sender has sent in the send packet. Sometimes like it can even arrive out of order. Okay, in that situation the receiver window size is also same, so it can store until they are delivered. Okay, So that is what, like, however, we can see that this is a quite reliable protocol because I am not increasing the burden for the network load. As well as you can see that the selective repeat protocol is storing whatever is the information which are received in a correct order, or I mean in a correct way. Okay, and yeah, after storing it will forward it to the application layer. Okay, then we'll talk about something called as timer. I didn't tell anything about timer here. Okay. Now we left with the timer concept here. See, theoretically what happens, selective repeat protocol, it uses one timer for one outstanding packet. Okay, theoretically I'll tell, but practically it is not at all possible, right? That means for keeping one timer for each packet, it is practically not at all possible, right? So here, practically we'll be having one timer. Okay, and when a timer expires, okay, that time only the corresponding packet, that means, like, say for example, I have 4 packets and timer I have on, and within the timer duration I have not received the acknowledgement. No acknowledgement is received and timer is also expired. Okay, so here the sender will resend only that particular corresponding packet for which the acknowledgement is not received. Correct. Okay, so in other words, if we try to see that go back n, that used to send all the outstanding packets as a group. Correct, no? So overall as a group it used to send, but here I could say that individually, that means your selective repeat protocol, it will treat it as a individual packets. Okay, and we know it is using only one timer. That means if a timer expires, then it will send only that particular packet. Fine. So this is how basically the timer concept will work, assuming that the timer will get expired for one packet, and after it expires, the second packet timer, I mean timer for the second packet will be set. Timer for a second packet will be set. Okay. Hope it is clear. That is why for this reason we make use of only one timer. Okay, and regarding acknowledgement, I think I have told you, like in case of go back n, the acknowledgement number was cumulative, right? Okay, that means it defines the sequence number of the next packet which is expected. That means which is confirming that all that previous packets are received. Say for example, if the receiver is telling that I want 6th number packet, okay, so receiver is giving a confirmation that 0 to 5 all are received safely. So sixth packet he is expecting. Who is expecting? Receiver is expecting. Correct, no? So here in case of selective repeat, the acknowledgement number, whatever is been sent from the sender, it defines the sequence number of a single packet. Right? So single packet which is received maybe like safe. I hope you are understanding. That means, let me take an example. Here, in case of selective repeat, say that second packet is sent to the receiver. Now receiver will send the sequence number of that particular single packet that is received safe and sound. Okay. Acknowledgement number you are sending for the second one, not what you are expecting. Right? And here there is no feedback for any other packets. Right? You're not giving any feedback. That means I want the third packet, I want the fourth packet. No, you're not giving something like that. You are acknowledging for the packet whatever you have received safe and sound. Is this clear? Is this clear what we are talking? In case of selective SR protocol. Okay, the acknowledgement number, it defines the sequence number of the packet received. Any doubt?
No, ma'am.
Okay. Somebody tell me how the acknowledgement number was in case of go back N. I said it is cumulative, correct? So it means that what is that concept of acknowledgement number in case of go back N? Somebody respond. Go back N ಅಲ್ಲಿ acknowledgement number ಯಾವ ತರ ಕಳಿಸುತ್ತೆ receiver? Hope you people are listening.
Yes, ma'am.
Huh. Somebody respond. Go back N ಅಲ್ಲಿ receiver ನಂಗೆ next packet ಯಾವ್ದು ಬೇಕು ಅಲ್ವಾ? That means whichever is the next packet which is expected, that information he will share it, which means that sender will get a clarity. ಈಗ ನಾನು 5th packet ಅಂತ ಕಳಿಸ್ತಾ ಇದ್ದೀನಿ ಅಂದ್ರೆ receiver ಇಂದ ಸೆಂಡರ್ಗೆ ಕ್ಲಾರಿಟಿ ಇದೆ. ಏನಂತ 0 to 4 ಎಲ್ಲಾನು ರಿಸೀವ್ ಆಗ್ಬಿಟ್ಟಿದೆ ಸೆಂಡರ್ ಇಂದ ರಿಸೀವರ್ಗೆ. So receiver is sending the acknowledgement number as 5th. That is the next packet. ಈಗ X packet if I send, X plus 1 is the acknowledgement I used to get. Okay. But in case of SR protocol, if I send X packet, I get an acknowledgement for X packet only. Clear?
Yes,
Nobody is responding. See, at least if you don't understand or if you are unable to talk, just let me know. Okay, ನಿಮ್ಗೆ ಅರ್ಥ ಆಗ್ತಿಲ್ಲ ಅಂದ್ರೆ ಹೇಳಿ. Now, this selective repeat protocol also can be better understood because this we are talking about one single sender and one receiver, and the case is not always true for multiple nodes and millions of networks, correct? So we need to go with the better analysis by using the finite state machines, right? So a simple finite state machine for keeping one sender and one receiver, or a sender and a receiver, we have this. Okay, so this is the FSM for selective repeat protocol, and as like go back N or simple protocol, Here also we have FSM at sender's side and at receiver's side. Clear? Anytime sender or receiver, initially they will start the system in ready state only. Okay, that means if I talk about sender here, let us talk only analysis about the sender's FSM. The sender will start in the ready state, but once it is started, they can be in the ready state or it can be moved to the blocking state. Okay, so it can be in two different states, either of the states, ready or blocking state. Now we will try to see the events which is happening. Let's say, for example, some particular event occurs. Now how the corresponding actions will be taken care whenever it is in the ready state or whenever it is in the blocking state. Okay, so first we will talk about the ready state. In case of ready state, the sender, whenever some event occurs, okay, say that here we have taken 4 events. Okay, so first event, if at all a request is coming from the process, okay, or an application, fine. So you are talking that you are getting, the transport layer is getting a request from the application layer. Then the sender will start creating the packet with the respective sequence number SN. He will store a packet. Okay, sender will store the packet and sends the packet. Okay, when it sends, the sender will start the timer for that particular packet and keep the SN ready with the next packet in the buffer, SN plus 1. Right? So this is the first event which is occurring, and these are the responses, corresponding actions taken by the sender. Now here you can see that if at all, can you see here? This is the line which you are taking. Okay, if the window size, okay, window is full, that is SF plus S size, SN is equal to SF plus S size. If it is true, okay, then it will enter into the blocking state. That means your window is full, sender cannot fill any more packets in the window. Correct, no? So it has to wait. Okay, wait is nothing but what? Blocked state. If at all the SN is not full, that means your window is not full. Okay, then if it is false, then again it should go to ready state. Okay, again make a packet, store it in a buffer, start the timer, send it, and the window will be, I mean, until the window is full. Hope you are understanding. Okay, and the second event, before it starts the second event, SN is equal to, okay, SN plus 1, wait for the second packet, and the value of SN is keeps on incremented, and it is incremented in the modulo like 2 power m. Okay, yeah, this is about the first event. Now let us talk about the second event. Second event, when this happen, let me talk. Say that an error-free acknowledgement is arrived, okay, that acknowledges one of the outstanding packet. Think that the sender has received an error-free acknowledgement for the outstanding packet of it window. Okay, that means buffer, it has stored some copy of the packets already sent. So one of the error-free acknowledgement is received. Now what it should do? It should mark that corresponding packet. If that acknowledgement number is equal to SF. SF is what? The starting packet sent. Okay, every time SF keeps on sliding. Correct, no? to the next packets after it receives the acknowledgement. So if at all the acknowledgement packet is equal to SF, they slide the window over the other consecutive acknowledged packets. Okay, that means the next packet which is to be acknowledged. So that will be slided over. If there are outstanding packets, okay, which are need to be acknowledged, again you restart the timer. Otherwise, stop the timer because you have received the acknowledgement for whatever the packets you have sent. You need to stop the timer. Yes. So this is the second event and the action taking place. When you see that there is a corrupted acknowledgement which is received, okay, the corrupted acknowledgement or an acknowledgement which is non-outstanding packet arrived. That means he was not at all waiting for that particular packet. I have a window size fixed. Okay, so I might have been like waiting for the acknowledgement for these sometimes. Okay, for these packets I was waiting the acknowledgement, but this is SN. SN is the packets which are which has to be sent next, correct? No, but I have received the acknowledgement for an outstanding non-outstanding packet. Why that is definitely it is of not required, correct? No, so that time what it should do, it should discard it. Okay, this is the third event. Next, fourth event at the ready state. What happens is whenever a timer expires, okay, it should resend all the outstanding packets in the window, reset the timer. Okay, so this is about the ready state. Okay, and here we'll talk about the blocking state. In case of blocking state, three events will occur, right? You can see here. Now what happens is, if at all there is an error-free acknowledgement arise, okay, that means blocking means what? Sender is waiting state. Okay, he has already sent many packets. Window is full. Now he is in the waiting state. Think that he is waiting and timeout occurs, right? If at all timeout occurs, then what he has to do? He has to resend all the outstanding packets and reset the timer. Say that a corrupted acknowledgement has received. He was waiting still, but he has not received a proper acknowledgement. What he has to do? He has to discard it. Say that whenever he is in the blocking state and he has received a proper acknowledgement. That means an error-free acknowledgement is received. That time, what he has to do? He has to check. Okay, if the condition is like error free, I mean here the window slide whether it is true or false. Okay, then move to the respective state. In that state these things will happen. Okay, so what it has to do, make the corresponding packet and whatever the acknowledgement is received, you check it whether it is expected acknowledgement. I mean, in case if it is expected, then slide over the window. Okay, and if at all there is any outstanding packets who are waiting for the acknowledgement, then you reset this timer, restart the timer. Otherwise, you stop the timer. Okay, so this is about the sender's FSM, finite state machine, for selective repeat protocol. When we talk about the receiver, again here you can see that receiver will be always in the ready state in the initially. When it is started, okay, it will I mean we don't have something called as block state or something here. Okay, at the ready state, three events can occur. Okay, an error-free packet with some sequence number let me talk about this case. We are talking an error-free packet with the sequence number inside the window is arrived. Okay. In case if the error-free packet is received, but if it is duplicate, then the receiver should discard it. Otherwise, store the packet. Store the packet. Okay. Second, after storing the packet, he has to send the acknowledgement with the acknowledgement number is equal to sequence number, not the sequence number plus 1. You can see the difference between go back n and selective repeat here. Okay, so acknowledgement number should be equal to the sequence number. And if the sequence number is equal to Rn, then deliver the packet and all consecutive previously arrived and stored packets to application layer, then slide the window. That means move that packets to the application layer and slide the window for remaining packets to send the acknowledgement or to receive. Okay. Second event, an error-free packet as received with sequence number outside the window boundaries. Okay. So in that situation, that means like you are talking that whatever the sequence number in the window, out of the window has received, that particular packet has received. Okay. That time here what happens? The packet is discarded because he has received out of the window packet. Okay, but an acknowledgement with acknowledgement number say that Rn has to be sent to the sender. Why you have to send, though you have discarded the packet, why you have to send the acknowledgement Rn? Because this is needed to let sender know that he will slide that window if some acknowledgement related to the packet, that is sequence number which is less than Rn, okay, is returned to the sender. Okay, that is why he will acknowledge back Rn. Okay. Now in case if the corrupted packet is arrived, which is an complete error, right? So that time the receiver should discard the packet. Okay, so these are all the things which happens at the receiver, and this is the FSM. You write it for receiver site for selective repeat protocol. Okay, so in case of window size, that is in case of selective repeat protocol, we can show that why the size of the sender and receiver window can be like almost like 1/2 of the 2 power m. Okay, almost we'll say that. That means though that the sequence number I gave 0 to 15. Okay, why I'll fix up almost like half of the window size I'm talking. Why it is fixed to 2 power, like half of your 2 power m. Say for example, I'll choose m is equal to 2. Okay, which means that size of the window is what? Size of the window 2 power m by 2 or 2 power m minus 1. Correct, no? So 2 power m minus 1, if you consider 4 minus 1, something like 3, right? Or else 2 power 2 by 2, which is equal to 2. So approximately we could take it as like half of it. Correct, no? Right? I can just show you the picture representation so that we can have a clarity. Yes. Can you see this diagram? Yes. Okay. So what we are talking about the selective repeat is the window size, right? I told you why it has to be like kept equal or like half of your actual packets which are sent. So just like your go back in protocol, Okay, in order to correctly discard the packet which is received duplicate or erroneously, so the receiver should correctly discard that particular packet. Otherwise what happens, if at all you increase the window size, okay, then possibility that the receiver may erroneously accept it and store it in its buffer. Okay, so that becomes a problem. Fine, say that the SF is 0, it has sent 0th packet. Okay, think that receiver has sent the acknowledgement, but it is not reached the receiver. Okay, it is lost. Sender has not received the acknowledgement, but receiver has sent. The same thing may happen for all the packets. That means like 0th packet it sent, did not receive. First packet, here the window size, what is that we have taken, like 2. Correct, no? 0 and 1. First packet it is sent, again the acknowledgement is lost. Okay, now what it will do? It will resend the packet 0 because timer out happens. So when the timer expires, it will resend the packet 0. Okay, in case if receiver has taken already 0, because receiver has already received 0 and 1, he has acknowledged, but acknowledgement has not reached the sender. Correct, no? So again the sender will resend the packet 0. So what the receiver will do, already he has taken the 0, and if he is getting the duplicate packet of 0 again, he will correctly discard it. Correct, no? If at all you fix the window size equal to 2 power m minus 1, or it is half of your actual size. Right, here it is 4 and the window size is 2. But other condition, here let me take. Here what is the sequence number, 0 1 2 3, again 0 1 2 3, like that. This is the packet. Now I have fixed the window size. You consider that the window size is greater than, that means it is 3 here. Okay, now what may happen if it is like greater than 2 power m minus 1. So 2 power m minus 1, like m is equal to 2 I have taken here. Okay, and 2 power 2 minus 1, if you take it as like 3. Okay, if it is like, if 3 is greater than whatever the size of your information or the sequence of your information, what happens? 0 is sent, first case. Acknowledgement is sent, 0 is received by the receiver. Acknowledgement is also sent but not reached the sender. Similarly, 1 is sent. Okay, but acknowledgement is not received by the sender. 2 is sent. Okay, again acknowledgement is not reached. Now what is the possibility? Your window size is 0 1 2. Okay, 3 is the window is full. Since the window is full and no acknowledgement is received, again 0 will be sent. Okay, now what happens is, thinking when the window slides over here, okay, in the window what is happening is, when the window slides over, 0 1 and 2 is already received, and in the buffer what happens, he might be waiting for third packet. Okay, but he has received 0. Agree? He might be waiting for third packet, but second time he has received packet 0. But actually sender has sent first window size 0th packet. First window 0th packet he has sent. But what he will assume? He will assume that he has got the next sequence number 0. He will assume. Okay. So erroneously he will accept the data and store it in the buffer and waits for the next sequence to come. Right? So erroneously he will accept it and store it as a new data. So in order to avoid this, okay, the window size has to be half. That means like half or less than 2 power m. So which we call it as 2 power m minus 1. Any doubt? Any doubt?
No, ma'am.
No, ma'am.
Yes. I'll continue in the next class.
Okay, ma'am.
I'll answer your attendance.